Hello, and welcome to this calculus lesson where we start to put together a lot of the things we've learned about what derivatives tell us and what we know about functions, even back from pre-calc, and learn to graph a function. We're going to use a fairly simple example, but we're going to talk about all the important features you should include in the graph and how you can tell if you're using technology if you have the appropriate graphing window such that you're not missing anything. So we're going to work with the function f of x equals x cubed divided by 3 minus 400x. And I'm going to need the derivative and the second derivative of this function, so I've also got that written down here. But we have some guidelines for doing this. The first thing we want to do is find the domain and the range. Well, the domain, this is a polynomial. This is the same as 1/3 x cubed minus 400x. The domain of every polynomial is all real numbers. So the domain is all real numbers. And the range. Now, the range doesn't necessarily have to be all real numbers. For example, quadratics are polynomials, and their domain is either from the minimum to infinity or from negative infinity to the maximum. But this is a cubic polynomial. The highest degree is 3. So when we use the leading coefficient test from pre-calculus, and if you don't remember that, you can look this up. We see that when we have an odd number is the highest degree, which is 3 is an odd number, and a positive leading coefficient, this leading coefficient here is positive, we fall to the left and rise to the right. That's my end behavior. That's what we learned to call that. And what that means is to the left it goes all the way down to negative infinity, to the right it goes all the way up to positive infinity. So the range of this one is also negative infinity. The y values can go as low as negative infinity and as high as positive infinity. So there's no range and domain restrictions. Another characteristic of a graph that you always want to include and make sure you're looking at are the intercepts. So far we're just working with the function, not with the derivative. So we're going to work with the y-intercepts. And you learned this maybe a long time ago, even back when you first learned equations of line. The y-intercepts occur wherever x is 0. Because when you make a graph, y-intercept is on the y-axis, and every point on this y-axis has an x-coordinate of 0. Now, you're not going to have multiple y-intercepts, because if you did, you wouldn't have a function. You can have multiple x-intercepts, by the way, but not y. But this is, you use this piece of information, you find f of 0, and that will give you the y-intercept. So I get 0 cubed over 3 minus 400 times 0. And I get 0. So it turns out my y-intercept is y equals 0, or the point 0, 0. When x is 0, y is 0. I know that's on my graph. So that also is giving me an x-intercept. X-intercepts occur when the function value, or the y-coordinate, that is what the function value is 0. So you replace f of x with a 0 and solve. And in this case, we're going to use some factoring to solve. Because if you're solving it looking at a graph in your calculator, why would you be doing this to begin with? So we solve this one by factoring. I'm going to take out I get a greatest common factor of x. That leaves me with x squared over 3 minus 400. And in order for this to be 0, either x has to be 0 or x squared over 3 minus 400 has to equal 0. Well, we already know that when x is 0, y is 0. So one of my x-intercepts is 0, 0. But I need to solve this other factor being 0. So let's see. How do I get x squared over 3 minus 400 equals 0? Well, I can do this. I'm missing a middle term, so I can use the quadratic formula with b is 0, ax squared plus bx plus c. Or because that middle term is missing, I'm allowed to use this idea that I isolate the variable. And then I'm going to multiply both sides by 3, so x squared equals 1200. So x is, be careful here, you get positive and negative root 1200. You don't know, when you square a number, you lose the information about its sign, so you don't know if the number you squared to get this positive value was positive or negative, so you have to take into account that it can be either. And I do that and I get 34.641. So I know I want my X window to go at least to say 35. I'll put 34.64 there for now. Okay, so that is information you should have already known how to find about graphing a function, but it's a nice little review from pre-calc. And we're going to look now at what the next steps are. So the next steps, I'm trying not to go too fast here. We found the intercepts. Oh, we didn't look at symmetry yet. I skipped the symmetry step. We can do that right here. Let's take a look at symmetry. Symmetry is also, it's either even or odd. You may remember that from pre-calculus. So our function was f of x equals x cubed over 3 minus 400x. Now, this is a polynomial, and one of the tricks of polynomials, that's an understood one there, is if all the exponents are odd, your function is what we call odd. But by definition, an odd function is one where when you replace x with negative x, the result, when you simplify, is what you would have gotten if you put parentheses around this function and a negative in front of the whole thing. In other words, change this to a negative sign and change the subtraction to addition. So we're going to try that. We'll find f of negative x. We get negative x cubed divided by 3 minus 400 times negative x. When I cube a negative number, I get the opposite of the original value. So that's the same as the negative of x cubed over 3. And this is the same as plus 400x. And I can check and see what if I did the opposite of f of x. That'd be the negative of, you got to be careful of the parentheses. And I can see when I distribute this negative, I indeed do get what's here. So this function is odd. That tells me I have symmetry about the origin. If it's a cubic, so it might do something like this. I don't know. It goes through the origin, which we saw over here. But whatever it does up here, it might do down there, or it might go the opposite way. But we have the symmetry about the origin. If you fold it along the y-axis and fold it along the x-axis, you would have 1/4 of the function tracing the other quarter. So that's the pre-calculus review. Let's see what's next in our list. Find the first derivative and the second derivative. We have already found them. But then we need to use these to find the intervals of increase, decrease, and concavity, which is the next steps here. So we're going to use the first derivative to find critical values. Okay, so now on to finding the critical values. Critical values come from the first derivative, and they come from the first derivative either having a domain issue, which this is not. The first derivative's domain is all real numbers, or from the first derivative being 0. That will give you a critical value. So I literally write that equation and solve it. And I get x squared. I can use the quadratic formula, or because this is missing that middle, you can't just solve a quadratic by putting everything but the x squared on one side, unless the x squared is the only term with a variable. If you had x squared minus 2x minus 400, you'd have to use a different technique. You'd have to use the quadratic formula. But I can add 400 to both sides and isolate the variable. And now I have to be very, very careful when I take the square root of both sides to understand that I don't know what the original sign of x was before I squared it. There are 2 values of x that will make this true because it's an even root I'm taking. So x squared 4, so I get plus or minus 20 are critical values. I want to make sure, so now I know I want to go all the way out from negative 35 to 35 because my x-intercepts were at negative 34 point something and 34 point something else. And I also want to make sure I include positive and negative 20 because that's going to show me a maximum or minimum. Well, and I also want to make sure I show the y value. How high does what y values do I have to include? Sometimes you get these graphs, and I'll show you when we go to graph this, that cut off the top. So I want to find the function values at 20 and the function value at negative 20. And this will tell me something about what my y-axis window needs to be. So I do 20 cubed divided by 3 minus 400 times 20 here. And I do negative 20. I have to be careful. Negative 20 cubed divided by 3 minus 400 times negative 20. And when I do each of those, so for this one, for f of 20, I get 5,333. I get negative 5,333. Sorry, negative 5,333.33. Well, for f of negative 20, I'm just going to get the opposite of that because this function is odd. So I get 5,333.33 because negative 20 is just the negative of 20. So the function value is just the negative of this function value at 20. So you can do that in your calculator. You get that, and it comes out that way in your calculator. So I want to make sure, wow, my y values have to go to like, I'm going to make it like 5,500. No, 5500, yeah. 5,500, negative 5,500 to 5,500 if I want to see all this. So you always go a little higher than what you need. This is you could go to 5,400, I suppose. But that tells me I need to make my window pretty large to see these peaks. So now that's really all you need to determine the graphing window, kind of, but there are some other things you're going to want to know. Like, where is this function increasing and where is it decreasing? Because remember, you're going to try to sketch this. So there's two things we're doing. We're doing, can we make a sketch? And we're doing, can we find the right window to graph this in? This is really what you need to find the right window to graph it in, is the maxes and minimums and the intercepts. We've done that. The only calculus here is finding these local maxes and minimums. Now, if I want to sketch this, though, some things are helpful to know, like where is this function increasing? Well, a function is increasing where the first derivative is positive. So the function is increasing. Now, we're talking about so many other things. Functions, first derivatives, second derivatives, where, let me erase that. The eraser gets funny. Where f prime of x, the first derivative, is positive, and it's decreasing where the f prime of x is negative. So I make a sign chart, and I put my critical values. My critical values were my zeros of the first derivative, negative 20 and 20. And I test some values, and I can test some values where I can recognize that this function has this general shape because it's a cubic. Okay, that's one of the other things. But if I test a value less than negative 20, if I find f of negative 30, what I'm going to find is this function is negative. Or the derivative, what I'm going to find is, sorry, this derivative, it's the derivative shape I need here. I said function shape. The derivative is shaped like this because it's a quadratic. So I'm actually going to find that that's a positive value. F of negative 30 is positive. If I pick f of 0, I can see I get a negative 400. I can see that right here. Remember, because I'm f prime of 0, f prime of negative 30. Sorry, this is a sign test on the first derivative. Okay, we're checking for the sign of the first derivative. So this is negative, and the sign of, if I found f prime of 21 or f prime of 30, I'd find the sign of that derivative was positive. So here my function is increasing. So the signs of the derivatives tell me things about the function. From negative infinity to negative 20. And that is an open interval because the negative 20, it's neither increasing or decreasing. In decreasing, from negative 20 to 20. Oh, and increasing again from 20 to infinity. So that is going to help me sketch my graph. So increasing, I'm making a note of that, negative infinity to 20, 20 to infinity, and decreasing from negative 20 to 20. Now, I found the values of my local min and max, and that will actually even help me see where it's increasing and decreasing. F of negative 20 was a positive 5,333, and we'll see this when we start plotting. I'm going to plot some of these points and then sketch in the rest of the function. So that's the first derivative test. Now we're going to move on to the second derivative test to see where my function is concave up and concave down. Okay, now to look at where the function is concave up and concave down. Second derivative determines concavity. So if the second derivative is positive, you're concave up. And if the second derivative is negative, you're concave down. Now, what does concave up and down look like? Concave up looks like this. Concave down looks like that. Now, it doesn't have to be the complete U shape, but if it's got kind of a bottoming out, it's concave up, kind of a topping off, it's concave down. So I have 2x equals 0, add x equals 0. I find that. And this is f double prime of x equals 0 is a potential inflection point also, meaning where the function changes from concave up to concave down. It's only potential because just like with the maxes and mins, it only if the second derivative changes sign there. So this is a sign chart for the second derivative. And the 0 of the second derivative is at x equals 0. If I put in negative 1, f double prime of the second derivative is negative. If I put in 1 into the second derivative is positive. So here, because this is a second derivative sign chart, my function is concave down here and up here. So I'd expect to have something like this going on. Concave down first, concave up second. And we're getting pretty close to figure, and I do have an inflection point, by the way. So x equals 0 and f of 0 equals 0. The point 0, 0, the function on the function is an inflection point. So we're getting pretty close to being able to sketch this graph now. Critical values, increase, decrease. We looked at the extreme values. We've looked at the inflection points. There are no asymptotes. And now we've determined an appropriate graphing window, mostly from the intercepts. We'll look at that, the intercepts and the max min. So we have some key things. If we are to sketch this graph, how are we going to sketch a graph here? Well, we're going to look at a couple of key values and make sure we include them. Oh, sorry, I'm trying to erase and I'm looking silly. So let me erase this so I have some room to sketch. So I got a bunch of points I figured out in the beginning of the video. I figured out some x-intercepts, some y-intercepts, some maximums, some minimums. And let's kind of make a list of those points I figured out in the beginning. So I have intercepts, x and y intercepts. I had the y-intercept and also x-intercept 0, 0. And then I had x-intercepts at, I did not write them down. Oh, like negative 34.44. I had like negative 34 point something, y is 0, and then I had positive 34 point something. We're just sketching this, so y is 0. So I can put these points right on my graph. 0, 0, 34 points. And I'm going to have symmetry. So I really have to draw one side of the graph. I have odd symmetry here. So, and have I drawn that point in exactly the right spot? No, let me erase one of these. Oh, sorry. So I haven't drawn that point quite in the right spot. I haven't quite got symmetry there, but that's partly because I'm also sketching this by hand instead of on a piece of graph paper. But really, it doesn't matter that we do this to scale. So this is negative 34 point something. I seem to have lost where I wrote that number down. And this is positive 34 point something. And this is 0, of course. Now, another thing I had was local mins and maxes at negative 20 and positive 20. I had the value negative 20, positive 5,333.33. And I had the value positive 20, and I go down about the same amount, negative 5,333.33, to be exact. 0, 0 was an inflection point that's already shown. I saw that my function was increasing from negative infinity. So I'm going to start drawing the function. I'll do a different color here. From negative infinity. So from negative infinity means I start down here to this point where I had this maximum. And it was decreasing. And I had this little twist. So an inflection point, I'm concave down there. And I come down. And I kind of don't twist to concave up until I get there. And then I go back through here, because my function was increasing there. That's an approximate graph. And now if you were to do this in a viewing window, let me show you what I mean about the viewing window issues. Right now I have this function graphed in Desmos, but I can't really see it. I just see this red line here. It looks like nothing. Well, that's because my window is not very good. As I zoom out, I start seeing more lines. So you want to make sure, so I'm going to go to settings here. And I'm going to make my x-axis go from negative 30. I'm going to go from negative 40 just to make sure I see everything. Remember, I have those 34.4 and negative 34.4 to 40. I have to do that. Oh, now I'm seeing all my intercepts. And my y-axis from negative 5,500. Whoop, it didn't believe me. Let me try that again. Negative 5,500 to positive 5,500. And this is giving me a positive, sorry. Negative 5,500 to positive 5,500. Now, sometimes you graph things in your calculator, say, but I can't see it. It's because you haven't got the window set right. So I go back to this graph, and I can see everything. I can see the maximums, the minimums, the intercept. You can see this little bit of it's concave down, going down here. And then, oh, there's that little twist at 0, 0. That's an inflection point. I hope you have found this video helpful. It's lengthy. I apologize. I should have broken it into parts, but it does review some of the pre-calculus things some of you are struggling with. Please email me your questions. Thank you.